In this video, we will do the Gauss Jordan elimination to this matrix. Notice that this matrix is the augmented matrix of this system. But the process of Gauss Jordan elimination is independent of the fact that the matrix comes from a system. Then let's use like a horizontal line and a vertical line. The horizontal line starts here and the vertical line starts here. And then we look at the first column of the matrix that is underneath this horizontal line and to the right of this vertical line. To this matrix, we look at the first column. And we look for a pivot. We have to pick a pivot in this column, if any. In this case, we have a pivot, and then we can use this as a pivot. Then we use this as a pivot, and then the next step says, use that pivot to make this a 0 and to change this to the 0. We can do that by changing row 2. We change row 2 by adding -2 times row 1. And we can change row 3 by adding to it negative row 1. When we do that, we will get the matrix. This one doesn't change, this row doesn't change. And then I'm going -2 times this row plus this, then I have a 0. -2 times -1 is positive 2 plus 1 is 3. -2 times 2 is -4 plus 1 is -3. And -2 plus 8 is positive 6. For the next row, we do -1 plus 1 is 0. -1 times -1 is 1 plus 1 is 2. Here we do -1 times 2 is -2 plus 0 is -2. And here we get -2 times 1. Sorry, -1 times 1 is -1 plus 5. This is positive 4. Okay, we have this. Now we move the horizontal line and the vertical line. We move it here. We move this line here and this line here. And we consider this part that is underneath the horizontal line and to the right of the vertical line. And we look for a pivot. Any non-zero number would be a pivot if you adjust it. In this case, this could be as a pivot. And I notice that I just need to divide the whole row by 3. And when I divide the whole row by 3, I still get good numbers. Then let's keep that one as an option. Then I'm going to divide by 3. That operation is denoted like 1/3 of row 2. I'm going to change row 2 by 1/3 of row 2, and then I keep 1, -1, 2, 1, 0, 1, -1, 2, and here I have 0, 2, -2, and 4. Now I will use this pivot to make 0 any other entry in that column. Then I will make this 0 and I will make this 0. I can make this a 0 by changing row 1. I'm going to change row 1 and I'm going to change it by adding 1 times row 2. And I can make this a 0 by changing row 3 by adding to it -2 times row 2. Then with these changes, I will get the second row doesn't change at all. Then I have 0, 1, -1, and 2. And then the first row, change it by adding row 2. Then I have here 1, 0. I'm just adding the 2 rows, 1, and 3. And for the third row, I have to add -2 times row 2. Then it would be -2 plus 2 is 0. This is 0, 0. -2 times -1 is positive 2 plus -2. I will get a 0 here too. And here is negative 2 times 2 is negative 4 plus 4. This is also a 0. Now what is the next step? I move this bar, and then I move it one to the right and one down, and I will get this horizontal line and this vertical line. And I try to find a pivot in this part that is left, but here there are no more pivots. There are no more pivots here. I move to the other column. Since there are no more pivots here, then I will move the vertical line one more to the right, and there is no pivots here, and then the matrix is gone, and then that means that I have finished. And then that means that this is already in row reduced form. Row reduced echelon form. Let's find the number R. Remember that R is the number of rows with a pivot. In this case, we have 2 pivots, and then R is equal to 2. D, the set D, are the indexes of the columns with pivots. Columns with pivots. And in this case, this is a set, and the set is 1 and 2 because column number 1 has a pivot and column number 2 has a pivot. And the set F is the columns without a pivot. And in this case, that set is column number 3 doesn't have a pivot, and column number 4 then is the set 3 and 4. Okay, now let's suppose that the intention of doing this row reduction was to solve this system. It doesn't have to be like that, but let's suppose that the intention were to solve this system. Then these 2 matrices are row equivalent. That means that the system associated with this matrix is equivalent to this system. Let me write that system. Then the system would be x1 plus x3 equal 3, x2 minus x3 equal 2. Then to solve this system, we decide which ones are the basic variables. We notice that the first variable that is here, once it's in row reduction, this is going to be called a basic variable, and this is a basic variable. Then in this case, we say that x1 and x2 are basic or dependent variables. And x3 is a free variable, is a free or independent variable. Remember, notion here where they're emphasizing basic, dependent is the same, free or independent. Then the goal is to solve for the basic in terms of the free. Let me do that. Then how can I, let's forget about this part here. We already did this part. Then solve for the basic. Let me write that down. Solve for the basic or dependent variables in terms of the free variables. Then what do we get? We get that using this equation, we get that x1 is 3 minus x3 and x2 is 2 plus x3. Now this is the solution, but we don't want to see the solution like this. We want to see the solution as a set. Then what is x1? x1, remember, the solution set is going to be a vector with 3 entries. In the first entry is going to come x1, but x1 is 3 minus x3. Instead of x2, this is x2, 2 plus x3. And the free variable just can be any number. Then we have that this is the solution set, such that x3 is a number. Notice that if I want to pick a particular solution, I can make x3 any number that I want. Just as an example, if x3 is equal 1, what example did I get? I get 3 minus 1 is 2, 2 plus 1 is 3, and here is 1. Let's see if this is a solution. Remember that this means x1 equal 2, x2 equal 3, and x3 equal 1. Let's replace here. What do we have? x1 equal 2. 2 minus 3 plus 2. What is this equal to? This is 2 plus 2 is 4 minus 1 minus 3 is 1. What about this? 2 times 2 is 4 plus 3 plus 1, and this is equal to 8. And here we have x1 plus x2. 2 plus 3 equal 5. Then this is the solution set. Here we have a collection of infinitely many solutions, and with that infinitely many, we can pick as many as we want. For example, if I pick x3 equals 0, I will be getting this vector, which is 3, 2, 0. And then that means x1 equals 3, x2 equals 2, x3 equals 0. Let's check that this is in fact a solution of this. It will be 3 minus x2, which is 2, plus 0. And this is equal to 1. Check. 2 times x1, 2 times 3 is 6, plus x2, which is 2, plus 0. This is 8. And here we have x1 plus x2. We have 3 plus 2, which is 5. Then we have checked that this is also a solution. We can pick any value that we want. We can pick x3 equals square root of 2, and you can do the same procedure, and you can check that the vector that you get, which is 3 minus the square root of 2, 2 plus the square root of 2, and the square root of 2, you can check that if you make x1 equal 3 minus the square root of 2, x2 equal 2 plus the square root of 2, and x3 equal the square root of 2, that this is a solution of that system. By the way, in this case, if we ask ourselves, is this a consistent or inconsistent system? Remember that it's inconsistent. Inconsistent means no solution. But this is not the case. We have infinitely many solutions. That means that this system is consistent. And consistent means either infinitely many solutions this is the case, or it means only one solution. But this system is consistent. Please do this homework.